The name of this lesson is Riemann sums, the fundamental theorem of calculus. Riemann sums is going to give us a shorthand notation for doing what's known as numerical integration. For you, it probably means the left hand and right hand method of finding the area under a graph. We're going to have a shorthand notation, which is going to be most valuable to us. And so that's what one part of this lesson is about. The second, the fundamental theorem of calculus, is going to give new meaning and usefulness to the antiderivative. So in this lesson, we will not be so much focused on working problems, but developing new tools that we can use throughout our future topics in the calculus curriculum. So we're going to look at a graph of the function f of x equals x squared plus 1. We're going to look at it between 0 and 1, okay? Just a small part of the graph is what we're interested in. So here it is greatly enlarged, I like to think, under the microscope. So with this distance is only 0 to 1. It's not a very big area. If you really stop and look at it, and it goes up only to 2. So this entire area is only 1 by 2, or 2 square units. What we're interested in is finding the area under the graph. And what we're going to do is we're going to first use the left-hand method. Now, if you've not had the left-hand method or right-hand method, we're going to use this. This probably will serve as a great way of teaching you the left-hand and right-hand method. But hopefully you've already had that, and it will serve as to reinforce those two methods. Now, we're going to use 10 rectangles. That is, n is going to be 10. Now, we're only going from 0 to 1. So remember, we need b minus a. That's the star. That's the engine that makes the left-hand and right-hand method work. So b minus a over n is 1 minus 0 over 10, or 1/10. Okay? So this is a graph of the left-hand rectangles. Remember, with the left-hand method, we start at 0. So our first rectangle is this rectangle right here. Then we go over 1 unit. What's 1 unit? 0.10. So we go over to 1/10. This is the height of my second rectangle. And of course, all the rectangles have the same width. We go over another tenth to 2/10, then 3/10, all the way up to 9/10. Now, the left-hand method does not, it stops there 1 unit short. It doesn't use the right endpoint, remember. So this is what we have. And so we want the area, find the total area, or that is the sum of the areas of these little rectangles. So what we do here is we simply, the height of each rectangle is written here, f of 0, f of 0.1. Now remember, f of 0.1 means a function is x squared plus 1. So we will square 0.1 and add 1 to it. And that gives us these values here up to 0.9 squared. So that's the sum of my heights. All of them have the same width. So we'll just multiply at the end by 0.1. We add these up, and we get 12.89, multiply by 1/10, and we get area is 1.289, which is an underestimate. Now, remember, we said earlier, the left-hand method is not necessarily an underestimate, but it is for a graph that looks like this. So that's the area under the graph using the left-hand method. We want to now develop the shorthand notation. Remember, said at the opening, Riemann sums, a shorthand notation. That's what we want to develop here. So let's write what we've just said here, which is the sum of these f of x's times b minus a over n, which is 0.1. This is a shorthand way of writing it. x sub I, where I starts at 0, that's our first rectangle. And we don't go to 1, we go 1 minus 1/10, or 1 minus 0/10. There's a reason I'm writing it like that rather than say 1/10. So this is a shorthand notation for saying exactly what we said here. Okay. And now, but this is the writing for n equal 10 and a equals 0 and b equal 1. Well, we know that n is not always 10, and our points a and b are not always 0 and 1. So let's put it in a more generic formula like this. So in the place of 1 minus 0/10, we're going to write b minus a over n here and b minus a over n here. By the way, this is a Greek letter. This is capital sigma, which we're going to use for summation. Okay, it's used throughout mathematics, modern day mathematics, for summation. So that's what we have here. Now, one more step. B minus a, that's the change, that's the difference of the x's. 0 minus 1, that's the difference of the x's. So we're going to call b minus a over n delta x. Greek letter D, delta x is b minus a over n. So we're going one step further, and everywhere there's a b minus a over n, we're going to put a delta x and a delta x. So that's where we are at this point. We're moving towards what we call the Riemann summation notation. Okay. Now, we could have used the right-hand method, and our graph would have looked like this, where we don't start at 0. We start at 0.1 for our first rectangle, 0.2, and then we do use 1 for the right-hand method, and that gives us that rectangle. Notice this is going to be an overestimate. Again, the right-hand method is not always an overestimate, but it is for this particular situation. Now, what we're going to do is just what we did before. So this won't take long. Instead of starting at 0, we start at 0.1, and instead of ending at 0.9, we end at 1. Each rectangle is 0.1 units wide. We put this into each of these into our calculator, or do it by hand or by inspection. It's not difficult to square these values, and it gives us these numbers right here. We add them and we get 13.85. All of them multiplied by 0.1. That gives us 1.385. And again, that's the area under the curve using the right-hand method, and that is an overestimate. And again, we could develop shorthand notation for the right-hand method. It's exactly the same as for the left hand, except what we do is we start out not at 0, but 1/10 over, which we're writing as 1 minus 0/10 as before. And now we're going to, everywhere there's a, since this is in terms of 1, 0, and 10, we want it in terms of b and a and n. So we will substitute b minus a over n here and here, giving us this. And then if delta x is b minus a over n, we will substitute delta x everywhere there's a b minus a over n, and that gives us this. Again, we're inching towards what we call Riemann sum notation. Now, if we were to increase the number of rectangles, two things would happen. Now, increase the number of rectangles means anything bigger than 10, say 20 rectangles, 100 rectangles. Be a lot of work. But the left and right-hand answers would get closer to being equal to each other, the bigger n gets. And here's even more important, we would be getting closer to finding the exact area. We have a note here. As you may have figured already, the concept of limits plays a vital role in the development of calculus. It did with the derivative, and it does with the antiderivative. Okay. Limits is most vital, most vital to the development of calculus. Now, one tweak further we want to make. If n is very large, well, how big can n get? Well, there's no limit to it, okay? In fact, infinity is the outer bound, okay? So saying n is very large is saying n is getting close to infinity. So let's see what happens as b minus a over n equals as n approaches infinity. Well, as the denominator approaches infinity, this thing goes to 0. Well, since we said earlier in the previous couple of slides that b minus a over n was delta x, if b minus a over n as n approaches infinity equals 0, that means that delta x approaches 0. So another way of saying n approaches infinity is to say that delta x approaches 0. So we're going to write our previous summation. We're going to write it like this. Instead of n approaches infinity, delta x approaches 0. And this should be, if you take, if delta x, that is the number of rectangles, approaches infinity, that should give us the exact area. So this is our all-important notation, which we call the Riemann sum notation. You might see it in various formats in different texts, but this is what we're using here. And so we'll move on. Now, the left-hand method gave us with 10 rectangles 1.289. The right-hand method with 10 rectangles gave us 1.385. One was an underestimate, one was an overestimate. Let's take the average of those two. And when we average them, we get 1.337. And I have a feeling that that's very close to what or closer to, let's say closer to what the actual area under that graph is than either of these two numbers. So let's proceed. Let's try something. We're going to suppose the antiderivative of f of x is capital F of x plus c. We're just supposing. Well, that means we have f of x is x squared plus 1 in our problem. We're still focusing on our initial problem from the very beginning. What's the antiderivative of x squared plus 1? Well, you add 1 to the exponent, gives you x cubed divided by the new exponent, which is 3. So that gives us this. And what's the integral of 1 dx? That's simply x plus c. So based on what we've said here, this is the antiderivative of this function. Now let's try something else. Let's put 1 into this function. Let's put 1 into this function and do the arithmetic. And when we do, we're going to get 4/3 plus c. Why did we choose 1? Well, remember in our problem, we're only concerned with numbers from 0 to 1. So we've put our rightmost point in, 1. Now let's put our leftmost point into this. And when we do, we just get c. Now let's take the difference of this answer and this answer. And when I do, I get simply 4/3. The c's cancel, 4/3. Well, what is 4/3? 4/3 is 1.3333 repeating decimal. Well, what did we get when we took the average with the 10 rectangles? We got that. They are very close to one another. Now, we've proven nothing, but I think we've discovered something. This is not a proof. This is just an interesting fact that we've discovered. Now, keep in mind, we said earlier, the difference between the derivative and the antiderivative. The derivative, you use the definition of the derivative to develop it. With the antiderivative, all we do is think backwards. We don't prove most of the tools that we use. But this is not a proof. But let's see if we can strengthen our assumption. This, by the way, we're calling the fundamental theorem of calculus. What it says, if f of x is continuous from A to B, and if when you integrate f of x, you get capital F of x plus c, that is, capital F of x is the antiderivative of f of x, then the antiderivative from A to B, in other words, A is our left limit, B is our right limit, is going to always be f of b minus f of a. It certainly was in the case we just saw, because what we did was we found the antiderivative, which was 1/3 x cubed plus x. And we put in our 1 and we put in our 0, and that's what we got. So this is a statement of what we just did. This is called the fundamental theorem of calculus. Okay. Now, let's see if we can help you make a believer of you. Look at the area. Look at the region I have graphed here. I have graphed f of x equals 8. That is y equals 8. And I've only done it from 1 to 5. And I want to find the area of this rectangular region. Well, what's its width? 4. What's its height? 8. What's the area? 4 times 8, or 32. Okay, that's just by geometry. The area of this region is 32. Now, let's apply the fundamental theorem of calculus. Let's find the antiderivative of 8 dx. And when we do, we get 8x. Okay, remember that function is y equals 8, or f of x equals 8. So this is our f of x, 8. The antiderivative of 8 dx is 8x. We're doing it from x goes from 1 to 5. So we're going to hang our numbers here just as a holding place. Now, what do? Let's put in 5. When you do, 8 times 5. Let's put in 1. When you do, 8 times 1. Now, 8 times 5 is 40. 8 times 1 is 8. The difference is 32. And look at this. That is the area. That is the exact area. So I have a feeling that our assumption earlier that we averaged the two using the left-hand right-hand rule, I have a feeling that then when we did that supposed situation where we found the antiderivative and got the answer of 4/3, I have a feeling that that answer was the exact area. But that's not enough. Let's go to this problem. We call this example 2. Let's find the area of this region. Now, this region is the line y equals x plus 6. In other words, y-intercept is 6, and we're looking at it from 1 to 7. Let's find the area of this region by geometry. Well, we have a rectangle here, and this rectangle is 6 units across. Okay, 1 to 7 is 6, and it's 7 units up. So this rectangle portion is 42 units. And then we have a triangle that is 6 by 6. So that's 36, and half of it, remember 1/2 base times height is 18. And so we have 42 plus 18 is 60. Well, now let's see if our fundamental theorem of calculus works. We're going to find the antiderivative of this, which is going to be x squared over 2 plus 6x. Here are our little numbers. Let's put 7 in for x. That's going to give us 49 over 2. And then 6 times 7, that's going to be 42. And then we're going to put our lower number in. That's going to give us 1/2. And this is going to give us 6. And we're going to take the difference of these two. Now, 49 halves minus 1/2 is 48 halves. And 42 minus 6 is 36. And then this is going to be what? 24 plus 36 is 60. Wow. So this is, again, not a proof. but it seemed to reason when we did the left hand and right hand that we did everything and we were heading towards that. And this is probably, when we did that antiderivative in 4/3, was probably the exact area. Well, we're going to go one step further and let you know it was not probably. It was the exact area. It is the exact area. We've used these two examples of things that you know for sure the area from geometry, and we have seen that the calculus bears it out to be true. So which means now if you had a problem like this, which you cannot do by geometry, the only way you could do this to find the area under the curve would be to use the left-hand, right-hand rule. But now we can use our technique, which is find the antiderivative of this, which is x cubed plus x squared plus 5x. Put in our 2 and do the arithmetic. Put in our 1 and do the arithmetic. This will give us 22. This will give us 7, and the difference is 15. And that is the area under the graph. Now, you might say, well, does that mean you never need the left-hand, right-hand rule? You do not want to throw that idea away for a number of reasons. We're going to use that type of reasoning to develop much of the future of calculus. And also, you're not always given equations that you're given data, and you're going to have to resort to a technique playing off of the left or right hand rule or something similar. And also, if you recall in an earlier lesson, we saw that there are some functions that no one has been able to find the antiderivative of, and so you would not be able to, if you can't find the antiderivative of it, you certainly can't use this method. But by and large, for most of the things that we will be doing in most of our calculus curriculum, this will stand you well. So what do we want to get from this lesson? We want you to know that whenever you get to this stage, this means this. This means this. In future courses, beyond first year calculus in particular, you'll get to this point often, and the instructor will say, this means this. So that's what we want to instill in your thinking. And the second thing is the fundamental theorem of calculus, which we will be using in introductory calculus, which this series of lessons is centered around, but also to a great extent in second, third year calculus courses. So this pretty much completes this lesson.